it's now time to turn our attention to dynamical systems. So one of the emphasis points of this book here on data-driven science and engineering, find everything here at databookuw.com. Lots of lectures, code, notes, everything that you need with a lot more lectures. But a lot of the emphasis on this book is around physical and engineering systems, physical science engineering systems, where dynamics plays a big role. And so part of what we want to start thinking about is how do I use neural networks in the context of dynamical systems? So in particular, I want to spend time talking today about thinking about structuring these neural networks, which are often used for things like image classification or speech processing, more towards understanding the evolution of dynamical systems and spatial temporal systems. So the objective here then is to come back to this neural network architecture and thinking about input layers to an output layer, where this is essentially a regression problem that I've kind of emphasized throughout, that this is nothing more than you give me an input, you give me a target, which is the output. The model is this structure. Find all the parameters that give me the best fit between that input and output. But now the way you think about restructuring this from the point of view of dynamics is that I want my input to be the state of my system. Now I'm going to think about x as the state variable, to be the state of my system at time t. My output is the state of the system at time t plus delta t. In other words, my input comes in, what comes out is the solution or the evolution of this spatial temporal system, let's say, or even just a temporal system, delta t into the future. Now notice that if I can train this, I give you data pairs so that I get an input and an output with these pairings, then the idea would be if you give me the state of the system now, I'm going to make a forecast for you. Here's what it looks like delta t into the future. Of course, I could feed that delta t solution in the future back into the network to get you 2 delta t into the future. Feed it in, 3 delta t into the future. And of course, we know forecasting is very difficult, so you know there's going to be a finite horizon where my prediction is going to hold. And in here, I've got, just like you would in a numerical stepping algorithm, you would get compounding errors each time you do this. However, the hope is that you can make some reasonable forecasts into the future using an architecture like this, where the interpretation of x and y over here is the state of the system now and the state of the system in the future. So that's how we're going to train our neural network. We're going to train it to do that. And so this is being used heavily across the sciences, these kind of architectures of learning spatial temporal dynamics. And so part of it is to learn how you can use different architectures to help you with that process. I will make a couple comments here. There's a nice connection to reduced order modeling that can happen here. You might have a very high dimensional system, and if you want to move to the future, you might also say, but I also know that there's a low dimensional embedding in this. So you might also do a dimensionality reduction through an autoencoder type structure so that you can move into a frame of reference in which you get dimensionality reduction and time stepping in that reduced variable. So these are all impositions on the architecture. Remember, as formulating this as a regression, as an input to an output with your model is this structure. So you can put in lots of different model types, one of them being one that has dimensionality reduction built in as part of the architecture. So those are the choices that you have as the constructor or the master architect of your own neural networks. Okay? So I want to learn then a time map. That's what this is going to do. And I'm going to give you a very simple example of it. It's so easy to execute actually in a neural network code, and you're going to find it's very effective. Okay. So by the way, let me also preface this with how would you learn a time map in the future? Normally what you do for learning a time map is you would do something like a numerical discretization and do a time stepper. For instance, an Euler step is a very simple idea, strongly related to this, because an Euler step takes you from t to t plus delta t. Runge-Kutz does the same thing. It has its own neural network architecture if you want to think about it as a neural network. So this kind of structure is very powerful and useful across disciplines. So here's the model we're going to actually play around with. Lorenz 63. So this is a very simple 3x3 differential equation. Slightly nonlinear in the sense that there's a quadratic term here in the second and the third terms. But this is a fantastic model because it produces all kinds of interesting behavior, including chaotic trajectories. So Lorenz 63 is sort of trivial to run. Put it in MATLAB, creates lots of trajectories or training data, and it's easy to simulate using something like fourth order Kutz. You can just simulate this and watch these trajectories very nicely. And what we're going to do now is going to take data from here and see if we can actually learn a time stepper. In other words, how can I train a neural network take me from time t to t plus delta t? And how does it compare to if I use a numerical integration scheme? Okay, so that's going to be the objective of this. And this is sort of, it's a toy problem, but it sort of gives you a lot of intuition about how this might actually work. Because most people know how to numerically solve this and have a very good feel for how you would do that. So the idea of putting this into a neural network architecture can be very helpful because you'll have some insight how to go about this. All right, so I'm going to show you some code. What we're going to do with this code is we're going to do a couple things. We're going to generate training data and test data. We're going to learn a model, and then we're going to take that model and see how well it does on the test data. That's how you would really evaluate how good your model really is. Remember, cross-validation is really critical in all of these things to do. Okay? So I'm going to walk you through the model. I won't train it here in real time, so I'll just walk through the model, and then I'll show you the results back on the screen here. Okay. So let's start off in the model. Simulate the Lorenz equation. So first of all, I'm going to go ahead and parameterize it. I'm going to start discussing about when I pull the data out. So dt here, it's not the time stepper I use. I'm going to use something like, in fact, I'm going to use OD45 to run this thing. And in running OD45, what I'm going to do is it's going to take whatever steps it wants for the kind of tolerance that's the default tolerance for the system. The dt here, though, is going to tell me pull the data out every 0.01 units of time. Okay, so that's when I want the time series back. I'm going to run it from 8 units up in time into the future. So give me every 0.01 units, 8 times into the future. Here's the parameters of the Lorenz model: 8/3, 10, and 28. The R being 28 means I'm going to be on a chaotic trajectory. So I'm in a chaotic regime, and I'm going to see a butterfly attractor out of this thing. Okay? So I have an attractor. I'm going to fall onto that retractor, and that's the parameter settings that get me there. So those are the parameters for Lorenz, and here is setting up Lorenz with some of the options. And in fact, what I'm going to do here with Lorenz is I define the Lorenz equations, which I already wrote the equations up on the board, so those are there, and so you can take a look at them in the previous slide. But there he is. That's the simple 3x3. Now, my ODE options, what I'm going to do is I'm going to really crank down the tolerance. So what I want to do is make sure that my time stepping is so small that my error is very small that's being generated from my time stepper. Notice that I'm going to pull out the data every 0.01, but what I want this is to be much bigger than the time steps that it would normally take to keep the error down here. Okay, so I'm seeing a coarse-grained time step because my tolerances are so low, I'm not going to refine it to model that kind of resolution down here. Okay, that would require much smaller time steps. This is going to be my training data. So I'm going to generate training data from this. Okay, so let's go ahead and start doing this. So first of all, I'm going to save all my data in input and output. And what we're going to do with input and output will be essentially all the values of x at time t. Output are going to be the values of x of time t plus delta t. They're going to come in pairs. So when I run these trajectories, I have a time series. And I just simply take, okay, this point here is my input. The next point in my time series is the output. And so I'm going to make 2 matrices of inputs and outputs. So one way to think about it, if I advance all of these delta t, I get to my output matrix. Okay? So that's how I'm going to organize the data. So what I'm going to do here then is do a loop. I'm going to do 100 training trajectories. Okay? So I'm going to take this simulation, run it 100 times. I'm going to generate random initial conditions. Here they are. I use the rand command, multiply by 30, negative 0.5. I'm going to show you what these look like in a moment. But the idea here is just to generate a whole slew of initial data, let them go. So initially there's a transient down to the attractor, and then they get stuck on the attractor of the Lorenz, okay? So I'm going to run it through OD45. Here it is. So you run it here, TY, OD45, call the Lorenz model, run at 8 units of time. My input is what it was before. In other words, I'm going to take all of this data, and then I'm going to make an input matrix, but then I'm running it 100 times, so I'm going to keep adding to that input matrix. So it's whatever it was before, so in the previous run, I'm going to take the first point to the next to the last point, where the output is the same as what was before, the second point to the last point. So remember, these snapshots from time 0 to time n-1 to time 1 to n, this is, the output is the input advanced delta t. So this is how you create these. So I have an input matrix and output matrix. They come in pairs. This is my training data. This is what I'm going to give my neural network to say, go figure out how to build a time stepper that maps those inputs to those outputs with these 100 sample trajectories that is given. Okay? So that's it. Now let's talk about how to build a neural network then. MATLAB, TensorFlow, Keras, these things all make it really easy to train neural nets. So here's what we're going to do. We're going to make a very simple neural network. Net equals a feed-forward network. 3 layers, size 10, 10, 10. I just made that up. Who cares? You could make 20, 10, 5. You play around with it. It's very easy. It doesn't take that much to train on this network. You can start looking at what happens in these things. And I just wanted to make 3 layers just to show you also that there's these different transfer functions that can happen between layers, nonlinear transfer functions. Net layers 1. In the first layer, do a transfer function, which is a log sigmoid. Net layer 2, do a transfer function, which is a radial basis function. Net layer 3, do a transfer function that's purely linear. That's it. So I just said, here's my network architecture, here's my activation functions, and now the only thing left is net. And see how easy this is to do. Look at that, one line. I'm going to train my neural network. Training it with the train command. Train that network that you just defined, input to output. In other words, here's what goes into the neural net, here's my target. That's it. Here's the network architecture, here's the data, train. And what it's going to give me out is this object net, which is a trained neural network. Now with this trained neural network, if I give it new data, it will take me from time t to time t plus dt, delta t, learned from those trajectories in input and output. Okay, that's it. Now this will take a little time to train, so I won't run it here in real time. You know, we'd wait 5 minutes and I'd have to tell you jokes. I don't want to do that. Okay, but there you go, train. I'll show you the results in a minute. And then what we're going to do after all of this, we're going to say, okay, fine, I trained it. How well does it work? So here's what we're going to do. We're going to make some new data. So this is where we start to see how well it works. Here's the new data. Make up some new initial data, randomly generated. Again, run it through the Lorenz. So this is not in the training set. So this is in the test. This is now, I'm just making up test set as I go. I have a new trajectory. It wasn't used for training. How well did it do? Well, I can plot what that trajectory is. And then I can take that same initial condition and run it through this loop right here, which is, I'm going to go through this loop, and what I'm going to do is take that initial condition, throw it into network. My initial condition, let's say, is time 0. When I throw it into net, it's going to produce the solution at time 0 plus delta t. I record that, go back through the loop, put it back in. The solution at t produces the solution at 2t. Solution at 2t produces 3t, and so forth. So I just go through this loop, and I produce a trajectory purely based upon the network that I learned, that input-output relationship. And when I do that, I now have a fake trajectory, fake meaning it wasn't run by OD45, it's a trajectory that was learned through this mapping of input to output through the network, okay? Through this 3-layer network with these nonlinear activation functions. How well did I do? Okay? And in fact, I do 2 test trajectories just to show you. We could do it on a bunch of trajectories, but we won't. So let me just show you the results of this because I don't want to train here in real time. Just want to show you how it looks. So first of all, let's start here. This is what the training data looks like. Remember, I took 100 trajectories, and I just put them all on this map here. What the blue balls are is where the trajectory started. That's the initial condition. Those are all randomly generated. So here's the 100 randomly generated initial data. You can see the transients down onto this nice attractor, which is sort of the hallmark feature of the Lorenz 63 model. Okay? So there you go. You have that model. This is your training data. I want to feed this into my neural network. I'm going to feed the pairs of t to dt plus delta t, t to dt plus delta t. And I have lots of trajectories, so it has lots of information about how this thing is evolving in time. All of it's going to be fed into the network. And also a pretty large diversity of initial conditions. So we're going to put that in, and we're going to train it. After training, I'm going to test it. And here's the test set. So what I'm showing you here, first of all, the dotted lines are the trajectories produced from the neural network. The solid lines are a high-resolution OD45 solve that we do, which is, let's call it the truth. So what I really want to know is, how well does that dotted line stay on to its corresponding solid line? So here, 2 randomly generated initial conditions that are not in the training set, right? They're just, I made up some new ones, see how it works. So they both start pretty close by to each other, actually. And you can see that the solid lines and the dotted lines actually stay on each other for quite a long ways, and then eventually they fall off. But notice, both of them produce a very nice representation of the Lorenz attractor. If you want to see a little bit more detail here, this is the picture we should look at. What you're seeing here in these 2 different simulations is the Lorenz model versus the neural network. The neural network is in light blue. And notice in the first simulation, and again, these are just randomly generated, the neural network actually sticks the model really well all the way to about almost ×6, and then it falls off. But in fact, this looks a lot like the initial sensitivity to perturbations in the initial condition that would normally occur in the Lorenz, even if I had a slightly different initial condition running through my high fidelity solver. So it's amazing how this training is produced for me basically a time integrator that actually accurately captures many of the dynamics very much like you would in a high resolution, high fidelity numerical time stepping algorithm. In the second simulation, it just basically tracks it, partly because this thing is staying on one of the lobes for quite a long time. Eventually, if I let it go for a while, it'd also fall off. But this shows you something kind of interesting, right? So this has no knowledge of Runge-Kutta or even no knowledge of the dynamics at all. It just simply says, give me input-output pairs, run it through this model being a neural network architecture, find the weights that for the training data gives you the best fit from the input to the output, and now using it somewhere else, you can see that you actually do pretty well in doing and basically having a time-stepping algorithm, or a time-stepping function, right? I wouldn't say algorithm. Now that you have this, it's just a generic black box tool. Put in an initial condition, get out the solution delta t later. So this gives us high hopes, potentially, for thinking about, like, wow, can be used very nicely in a lot of architectures that are more common to the physical and engineering biological sciences, where we think about spatial temporal systems quite a bit. And this gives you a way forward, maybe, to think about doing integration and maybe even dimensionality reduction. So there's a lot of work going on in these directions around reduced order models and time-stepping schemes that are more accurate even than some of the coarser methods that we have available to us, because you can build them here with neural networks given a good set of training data. So again, I'll highlight that this along with other lectures as well as all the code can be found at databookuw.com, all the code in Python and in MATLAB, as well as the notes itself can find here. A PDF file is there. Lots of other lectures for this, and this is all coming from Chapter 6, where we're talking about neural networks. I want to emphasize again, the neural network is nothing more than just a regression to a functional form that has composition. That's all it's really doing. And so I just want to emphasize that there's no big magic there, but this compositional structure, which is very large, has amazing capabilities to express functional solutions. So it has this universal approximation capabilities that you can see here does an amazing job at capturing the dynamics of a dynamic system like Lorenz 63.